Good morning, everyone. Hi, students. In this lecture, I am going to discuss first pushing and pulling. So, pulling is easier than pushing. So, how to justify this? And next, it is a rough inclined plane. Let us see first one. Pulling is easier than pushing. See how to justify this? Right. See, coming to pushing. So, we are taking a block on a rough surface, which is a horizontal. Now we are pulling the block. You can say applying force at some angle theta with a horizontal. So in the last lecture, we have discussed find minimum force to move the block, right? So there we got result. If this theta equal to angle of friction, we can move the block with a minimum force. See here what happens when we are pulling the block. So when we are pulling the block, we are having one component along vertical. It is F sine theta. And along vertical, there is no net motion, means there is no net force. Because there is no motion along vertical, that means normal reaction plus F sine theta should be balanced by mg. That means normal reaction equal to mg minus F sine theta. See here what happened. When we are pulling, normal reaction is reduced. Before force was applied, normal reaction was mg. Now when force is applied, normal reaction is mg minus F sine theta. Okay. That means now normal reaction is reduced. So when normal reaction is reduced, limiting friction will be reduced because it is equal to mu s into normal reaction. So less normal reaction, less limiting friction. That means with less force, we can move the block by pulling. Okay. But if you observe, when we are pushing, the block, see what happens. So when we are pushing the block, so applying force like this, its one component is now along vertically downwards. One component is, that means in pushing, normal reaction is increased. Okay, applying force like this, what happens is one component is now vertically downwards. So because of pushing, normal reaction is increased. Therefore, limiting friction increases. So it becomes difficult to push the block. That's why pulling is easier than pushing. Okay. So in pulling, we have seen that when theta equal to angle of friction, we can pull the object with a minimum force. Right? Let us see here one more case. That is while pushing. So assume we are pushing a block. We are pushing a block. We are pushing the block. Suppose a force is F. It makes an angle theta with vertical. It makes an angle theta with vertical. See the condition to move the block. F cos theta vertically downwards, right? So first focus free body diagram. F cos theta along vertically down. Mg downwards. F cos theta also downwards. Normal reaction upwards. Since there is no motion along vertical, normal reaction must balance mg plus f cos theta. mg plus f cos theta. Okay. Right. Now to move the block, condition is f sin theta should be greater than or equal to limiting friction. Limiting friction is now mu s into normal reaction. Normal reaction is mg plus f cos theta. Okay. Right. Now see expression for f. F should be greater than or equal to mu s mg upon, we have taken this one to left side. So sin theta minus mu s cos theta minus mu s cos theta. Students, see carefully here. Denominator should not become zero. If denominator becomes zero, this total value becomes infinite. That means we have to apply very large force to push the block. The meaning of infinite. So basic condition is denominator should not become zero. So here what we can write? We can write sin theta minus mu s cos theta should be greater than zero, because if it is equal to zero, infinite value, which is not possible. So from this, see what we can write: sin theta greater than mu s cos theta, or I can write here tan theta greater than mu s. Okay, and we are knowing that mu s equal to tan alpha, where alpha is angle of friction. That means if this angle is greater than angle of friction, then we can move the block. See once again, if this angle made by the force with vertical is greater than angle of friction, then we can move the block. If it is less than, then we cannot move the block. See carefully. Suppose theta f is along vertical. If we apply force along vertical, block does not move. Okay. Once this angle is greater than angle of friction, then only we can move the block. Okay. So here what we are saying, in case of pulling, we can move the block with minimum force when theta equal to angle of friction. Here, in case of pushing, if theta is greater than angle of friction, then only body moves. Okay. And why in pulling is easier means, because of pulling, normal reaction is reduced and hence limiting friction is reduced. So it becomes easy to pull. But here, because of pushing, normal reaction is increased. Therefore, limiting friction increases. So it becomes difficult to push the block, right? I hope you got clarity. Let us see next one, rough inclined plane. So we are discussing here angle of repose. It is the angle of inclination. It is the angle of inclination for which body is about to slide down. See carefully what is it? So taking a rough inclined plane. So taking a rough inclined plane. Suppose angle is a theta. So place a block on inclined plane. See how many forces are acting on the block. So focus a free body diagram, number of forces that are acting on the block, normal reaction, normal to inclined plane, mg vertically downwards. I am taking for mg two components. One is normal to inclined plane, that is mg cos theta, and one is a parallel to inclined plane, mg sin theta. Now see carefully, when we are increasing theta value, see here limiting friction, mu s into normal reaction, right? Normal reaction is mg cos theta. Now, if you observe carefully, if theta is increased, if theta is increased, sine theta also increases. That means this downward force increases. Now come here, a limiting friction. Mu s mg constant, remaining is cos theta. When theta is increasing, cos theta decreases. That means when theta increasing, downward force is increasing, frictional force means limiting value is decreasing. At one point of time, both are equal. When both are equal, block is about to move down or about to slide down. So I'm writing condition here. Suppose when theta equal to alpha, I'm taking alpha as angle of repose. Okay, angle of repose. When theta equal to alpha, what happens is downward force, that is mg sine alpha, is just balanced by limiting friction, that is mu s mg cos alpha. So here mg gets cancelled, right? So mg cancelled here. Remaining is now tan alpha is equal to mu s. So tangent of angle of repose, tangent of angle of repose is equal to coefficient of static friction. Okay. So we got same kind of result in case of angle of friction, right? Right. Let us see now here. So here what we can conclude, if if theta less than alpha, if angle of inclined plane is less than angle of repose, block does not move. Okay. Block does not move. Block does not move. Okay. So frictional force how much? Since the block is not moving, it is a static friction, right? So which is equal to mg sine theta, right? If angle of inclination is less than alpha, means less than angle of repose, block does not move. So since block is not moving, friction is static, which is equal to mg sine theta. Okay. Next, when theta equal to alpha, about to move, right? If theta equal to alpha, block is about to move. That means what I can do here, even I can take equal to also. Equal to block does not move. Equal to means about to move. Okay. Then also friction is static, which is equal to mg sine theta. Okay. Right. Now next case, if theta greater than alpha, then block moves. Then block moves. When block is moving, frictional force will be kinetic, which is equal to mu k into normal reaction, which is equal to mu k into normal reaction, right? So in this case, what happens? Mu k into normal reaction is mg cos theta. right? So first case, less than or equal to alpha, does not move, friction is static, it is mg sine theta. Greater than alpha, block moves. Since the block is moving relative to the contact surface, friction is kinetic, which is mu k into normal reaction. Okay. See, when block is moving down, net force, when block is moving down, net force will be, it is mg sine theta, minus mu k mg cos theta. Okay, when block is moving down. From this, I can say acceleration is g into sine theta minus mu k cos theta. This is when block is moving down. Block is moving down. Okay, right. Sometimes you will be given question like block is moving down with a constant velocity. Block is moving down with a constant velocity. Its meaning is acceleration is zero. Acceleration zero means sine theta minus mu k cos theta is zero. Then see what happens if velocity constant. So block is moving down with a constant velocity. Then a value 0. That implies a value 0 means sine theta is equal to mu k cos theta. Or I can say that from there, tan theta is equal to mu k. That means we are given indirectly coefficient of kinetic friction. We are given indirectly coefficient of kinetic friction. Suppose you are given like theta is 30 and condition given that block is moving down with a constant velocity. So you have to understand that we are given mu k value indirectly. Okay. Next, suppose block is moving up. Block is moving up. When block is moving up, friction will be down the incline. And since block is moving, friction is a kinetic. So net force will be, so when block is moving up, net force will be mg sine theta plus mu k mg cos theta. So from this, what I can say is acceleration is g into sine theta plus mu k cos theta. Okay. This is when block is moving up the incline. Okay. So these points we have to keep in mind because we have to solve problems basing on these results. Acceleration is g into sine theta minus mu k cos theta. It is when block is moving down. Moving down, friction is upwards. Velocity constant a0, tan equal to mu k. If block is moving up, when block is moving up, friction is down. Okay, this is acceleration. So this is regarding rough inclined plane. Okay, right. Let us see problems. See the first problem. So right. Now see the first question. A block of mass 2 kg rests on a rough inclined plane. Rests on a rough inclined plane of angle 30 with the horizontal. The coefficient of static friction between the block and the plane is 0.7. So angle of inclined plane angle is given and given coefficient of static friction, asking frictional force. So first we have to focus, is the block moving or not moving, right? Let's see here. So first write down given data, mass given 2 kg, angle of inclination given 30, mu s value given 0.7. We have to calculate frictional force. So just now we have learned that if theta less than angle of repose, okay, how to find angle of repose? Tan alpha equal to mu s, right? Mu s value 0.7. So from this we get the value of alpha, right? Alpha is tan inverse 0.7. Okay. So tan inverse 0.7 means just see once what is the corresponding angle. So here we got it is 30, right? Angle of inclination given 30. 30 means tan 30 equal to 1 by root 3. Tan 30 equal to 1 by root 3. And this value approximately 0.58. So from this what we can say? Alpha is greater than theta, right? Because alpha is how much? Tan inverse 0.7 and this is now 30. Okay. So when angle of inclination less than angle of repose, block does not move. Since the block does not move, friction is static, which is equal to mg sine theta. I hope you got the point. So what I am saying is here, so we are comparing the angles, okay? We got alpha is known, tan inverse 0.7, says 30. So angle of repose is more than 30. That's why block is not moving. So friction is static. See mass how much? Mass given 2 kg. G value 9.8. Sin 30 1 by 2. So F value how much? 9.8. So answer is it is option 1. So just focus angle of repose how much. Then we can decide is a block moving or not moving. Okay. See next one. An insect crawls up a hemispherical surface very slowly as shown. The coefficient of friction between the surface and the insect is 1 by 3. If the line joining the center of the hemispherical surface to the insect makes an angle alpha with the vertical, the maximum possible value of alpha. This is the question asked in 2001 for 3 marks. We have to find maximum value of alpha. And mu value given 1 by 3. Condition is, condition is it crawls up slowly. Slowly in the sense speed is almost zero. Okay. Let us see how we are solving. So first of all, see free body diagram for the insect. Free body diagram for the insect. See how many forces are acting on the insect. First of all, mg vertically downwards. mg vertically downwards. Normal reaction towards the center, right? This is now alpha. Just draw tangent at the point, at this point. Let us draw tangent at that point. So drawing a tangent at that point. Suppose that tangent makes angle. See how much? This is alpha means this also alpha, right? And if you observe carefully, it is just like on a rough inclined plane. It is just like a rough inclined plane. Condition given moving slowly. Moving slowly means along the tangent. Net force must be equal to 0. So along a tangent means I can take here weight component, right? mg sine alpha. Weight component along the tangent. If this is balanced by frictional force, then we can say it is moving slowly. When alpha maximum, see carefully, when alpha maximum, see carefully here, as insect is going up, alpha increasing means mg sin alpha value increasing, limiting friction, limiting friction is decreasing, mu s into mg cos alpha, this is decreasing. When alpha becomes maximum, both are equal. So mg is sin theta equal to mu s into mg cos alpha. When alpha is maximum, mg gets cancelled. Tan alpha equal to mu s. Tan alpha equal to mu s. And mu s given how much? Mu s value is given 1 by 3. That means I can write here cot alpha equal to 3. So just compare with that rough inclined plane. So it becomes very simple. That means answer is now option 1. Right? See the next problem. So focus carefully. See what is given. A block of mass m is on an inclined plane of angle theta. The coefficient of friction between block and the plane is mu and tan theta greater than mu. Condition is tan greater than mu means mg sin theta greater than mu mg cos theta. Okay. The block is held stationary by applying a force P parallel to the plane. Block is held stationary by applying a force P parallel to the plane. The direction of force pointing up the plane is taken to be positive. Direction of force pointing up the plane is taken to be positive. As P is varied from P1 to P2, P1 mg into sin theta minus mu cos theta, P2 mg into sin theta plus mu cos theta. The frictional force versus P graph will look like, see diagram, and we have to verify the options. So we have to focus very carefully how we are going to solve this. So first write down range, range of the force. So it is given that applying force, it is like this P, applying from where to where? P1 mg into sin theta minus mu cos theta and P2 mg into sin theta plus mu cos theta. Okay. So we have to decide force, right? Frictional force. So here what I am saying is to understand easily, let us take values. Okay. So I'm taking here for mg sin theta, I'm taking a value for this. mg sin theta Take it as 20, 20 Newton. And I'm taking limiting friction, that is mu mg cos theta. Let us take it as a 15. See why I have taken mg sin theta value more. Reason is condition given that tan theta greater than mu. Its meaning is mg sin theta greater than mu mg cos theta. Then we get tan greater than mu. That's why I have taken this is 20 and this is less than that value. Okay. So just I have taken values randomly to understand easily. Okay. Now see carefully. If no force is applied, if no force is applied, what happens? mg sin theta 20. Frictional force is limiting value 15. So since it is dominating, it will move down. It will move down. And net force how much? 20 minus 15. That is net force. Now condition is given that block is kept at rest. Okay. So now what I am saying is 20 down. I will make diagram separately here. 20 downwards. This we cannot change. It is a fixed. Applying force P upwards. I am taking here, okay, upwards, P upwards. Frictional force. Frictional force depends on these two forces. 20 fixed. Frictional force limiting value 15, right? Limiting value 15. So I'm taking this as F. I'm taking this as F. This may be up or may be down, okay? Now condition 1. Suppose P equal to 0. No force is applied. Block will move down. So frictional force how much? 15, right? Okay. Let us take, I am applying a force here, 5 Newton. How much? 5. Since it is now 15, if I apply 5, 5 plus 15, 20, able to balance this. Block does not move. Okay. Now see carefully. When P value, I'm making a table here to understand easily. And if P value 5, okay, applying this force upwards, friction will be 15. So sum equal to 20. 5 plus 15, 20. 20 and 20 balanced. Suppose I am applying here 6. When I apply 6 here, what happens is friction will adjust. It is a static, okay? It will adjust. So it becomes now 14. So that applied force is 6 upwards. Frictional force is 14. Total is now 20. So this is 20, this is 20 balanced. Let us take, we apply 7 Newton. Then friction becomes 13. If I apply 8 Newton, friction becomes 12. See carefully, when we are increasing the force, frictional force decreasing, right? Now, if I apply 20, frictional force will be how much? 0. What the point? Because sum must be equal to 20. Sum must be, right? If I apply 21, see what happens. If I apply 21, frictional force, sorry, this applied force 21, friction becomes minus 1. So what is meaning of minus 1? We have taken up the plane as positive, right? Minus 1 means friction is now downwards. It is 1. So that applied force 21, this is 20, friction is 1. So total becomes 21. If I apply 22, friction becomes minus 2. Means again value increasing but direction is opposite. So if I apply 35, why 35? Because according to these values, this value will be 35, right? Mg sin theta 20, mu mg cos theta 15, total how much? 35. So if I apply 35, friction will be limiting value, becomes a 15. That means when F is, sorry, When P is increased from 5 to 35, frictional force decreased, becoming 0 when P equal 20. After that, if you still increase frictional force, value will be less but direction reversed. 1, 2, like this up to 15. Direction is downwards, up from here. Up to here, friction was upwards, right? That means up to some time, friction positive decreases. After that, friction negative increases value wise. See options. So up to some time positive. So first of all, we can eliminate B and D because friction is not a constant. Next, first positive, then become negative. First negative, then it is positive. But what we got? First friction is positive. Okay. That means option A is correct one. So I hope you got clarity.